the Z transform. Okay, so maybe I take an example here. It's just a convenient way of writing the filter. So let me take an example here. So if I have, for example, h of n equal to, okay, I'll use this notation now. So it is sequence. When I write sequence, maybe I write, let's say 1 over 2, 1 over 2. And so you think about the sequence like, so that like, you look at this guy blocking. So I write the h here in the sequence of 1 over 2, 1 over 2. And I need to know where is the origin. Right, where's the origin? So the notation sometimes I use is I just put a arrow here. So that is the origin, right? So this is where n equal to 0, and then you know that the next one is n equal to 1, and so on. And outside that is 0. Okay, so that is a convenient way of writing a finite impulse response filter, FIR filter. Okay, so if I have that one, then the HZ just simply equal to 1 over 2 plus 1 over 2 Z minus 1. Okay, so that is an FIR filter in the Z domain. Alright? So that's okay. Another one, example 2 here. So now I have this filter Hn. But now I make it a little bit more complicated, and I make it equal to a to the power of n, a to the power of n, maybe I put here, if n greater than or equal to 0 and 0 else. So that is a second example of another filter. So this thing here is going to be a signal, so you see that as, let's say A is some number less than 1. So at n go to infinity, the signal will keep decaying. But this thing, you agree that it's going to go infinity, right? Maybe I can move this thing around. Okay, Z transform of this. By the way, what I can do is I can write this signal maybe in a more compact form. Is equal to a to the power of n un. So un, where un is simply equal to this so-called unit signal equal to 1 when n bigger than equal to 0 and 0 else. Can you still see in the back? No? Okay. So this signal here, you see that I have this a to the n, and I simply multiply with this cutoff signal, which is only let the thing from n from 0 towards infinity. Okay? So I have that signal. Now let's see what is the Z transform that signal. So example 2, continue. So to compute the Z transform, I'm now going to deal with SZ now equal to the summation when n goes from 0 to infinity, and I just plug into that signal, right? Because when n from, I have this summation from minus infinity to plus infinity. But from minus infinity to minus 1, n equal to 0. So the sum doesn't contribute. But from there forward, so from 0 to infinity, and I have a to the power of n, z minus n. Okay? Now this thing here equal to the summation, I can put them in and go from 0 to plus infinity, and a z minus 1 to the power of n. And you recognize this is just simply a geometric sum, right? This is a geometric sum. So you know that this thing here we're going to be equal to, is equal to 1 over 1 minus AZ minus 1. Is that okay? There's some condition. Okay, someone already remember this. Yeah, I can only write this if and only if the thing inside here, the absolute value of this is strictly less than 1, right? Otherwise the sum blow up. So this is only if the absolute value of z, so this thing here is less than 1, or the absolute value of z bigger than absolute value of a. Okay, and this thing here, people call, what is this? The region of conversion. So that is the region of conversion. So that is the region of conversion of the ROC. But you can see what I have here is I have a signal which is infinitely long, but in the z transform, it have rather nice form, right? You can write z over z minus a. It have rather nice form, right? And you can see later on that this kind of thing actually describe some of the system like this. Okay. So who already heard about this region of conversion before? Okay, so quite a few people, and it is just simply the concept in the z-plane, right? In the z-plane, maybe I can draw them here. So here the z-plane. A z-plane is a complex plane, right? So the z-plane, and it has the real part and then imaginary part, and maybe let's say here the A sitting here somewhere, and the region of conversion of this particular filter is just anything outside. Okay. So and I led here this exercise. So for those one that haven't done Z transform before, I recommend you to try this. Now I consider another system, Hn, but now I take it equal to maybe minus a to the power of n u of minus n minus 1. I recommend you to look at these systems as a homework and to verify that this thing here also have a z. You can do exactly what I have. The z equal to exactly the same. Exactly the same. That's kind of. Except the only thing that I can distinguish between these two systems is now the ROC is when z less than a. Okay. So now that's kind of giving you two simple systems, both of them representing an infinite impulse response system, an IIR system, but having a very simple Z transform, which in turn allows us to do simple computation. So, clear so far? Okay. So now that we attack these systems, Now see, I'm going to go back and look at these difference equations. I'm going to look at these difference equations, and you understand where it comes from, right? Because of this simple way of implementing it. But now let's see if we can analyze these systems. So I assume, right, it is not hard to imagine. The Z transform is a linear transform, right? It has all the properties I will not go through. But because of that, it's a linear transform, so I can really take the Z transform of this simple equation, both sides. Right? So let me do that. So typically we take this